Hello, everyone. Uh, Thanks again for joining us for this webinar. This is part two of our webinar series on creep. And this one specifically talks about insights from creep testing of service exposed components. So in the first webinar 2 weeks ago, we talked about basics of creep, how to design for creep, and how to perform remaining life assessments of components operating in the creep regime. Now, one thing that we didn't talk about 2 weeks ago is how creep testing aids in the remaining life assessment. And that's what we are going to discuss today. So we have a creep lab in our Cincinnati office, and I spent a lot of time on creep testing and remaining life assessment of high temperature components from the petrochemical industry. So I just wanted to share some of those experiences with you. So this is like a brief uh, this is how the webinar is organized. We first kind of talk about why we do creep testing of service exposed components. I want to spend a few minutes talking about field metallographic replication of service exposed components, just because that's often used as a predictive tool to look for creep damage. And then I'll move on to I'll spend some time talking specifically about the Omega testing, follow up with some case studies, and also talk about a, a few slides on the effect of microstructural transformations during testing. Now, this presentation, the way I have organized it, it assumes that you have participated in the first webinar, but some of the key concepts I will review anyway. So, so what's the need for doing creep testing? Because, as I mentioned in my last webinar, like if you're going with API 579, it provides you the creep properties of most of the alloys that are commonly used in the industry. And if you know the service history, you could take those properties and then do an assessment to figure out how much damage the component has accumulated during the past service and uh, how much more life it has. So that can be done. It can be a paper exercise. So what's the need for doing creep testing? Well, few reasons for that. One of them is that a lot of times we don't have a precise description of the operating history. So without that, you really cannot make any reliable assessments on the past damage. So that's commonly a problem where you don't have the good thermocouples, or you don't have good pressure data historically over the last 30 or 40 years. A lot of times these components have been in service for a long time, and you just don't have good information available. Now, another reason why you may want to do creep testing would be if you know that, let's say you have had a process upset where the temperature shot up really high, where at that point you don't really know if it has suffered any significant in-service degradation. A third reason would be, as I just mentioned, a lot of times some of these components have been in service for 30, 40, 50 years, while they're designed only for usually for 100,000 or 200,000 hours, so 10 to 20 years. So when you do a life assessment, even if you have a good idea on the operating history of the component, and you could do a 579 based fitness for service assessment. A lot of times when you don't actually know the properties of the material, you will have to have some conservatism there. So a lot of times you go with maybe the minimum properties that are given in 579, and when you use the minimum properties and do a paper exercise, you might find that the it'll predict that it has consumed all the useful life. So when you get there, if you could do testing, the testing will provide you creep properties specific to the component in question, and that's where the benefit comes from. And even when you don't have history, past operating history available, when you do creep testing, the test results will incorporate any past damage that it has accumulated during service. So you don't necessarily need to have a good understanding of the past history if you have the creep test results. So these are some of the reasons why creep testing is often employed when you do fitness for service of service exposed components. Now, as I mentioned before I go into the creep testing part, I want to spend a little bit of time talking about field metallographic replication. So I would think that most of you are familiar with the technique. It's a non-destructive technique used to determine the microstructural condition of metallic components. So what you do is you polish and etch in situ of a component, and then you replicate that microstructure onto an acetate tape, and then you examine that replica in the lab. So what you're looking at here, this is like a 5 chrome heated tube replica. Looking at the microstructure there, what you're looking at here is cracking. That's in fact type 4 cracking in a grade 91 weld. So you could now look at the surface microstructure under a microscope and make some judgments on the condition of the component. Now, one method that's commonly used that I've seen is this Noivos classification, which is this plot here kind of shows how that's done. So what you're looking at here is a creep strain versus time curve, and they are superimposing the kind of damage that you would see at different stages. So the damage parameters A, B, C, and D refers to, like, if A is like if you just see some isolated creep voids. B would be you now have some aligned creep voids along the grain boundaries. C would be you have like micro cracks. Now those aligned voids are linking together to form micro cracks. And D is you now have like macro cracks. So based on this, they have come up with what path they should be taking. So if it's just some voids, you could just observe it. Don't have to immediately act on it. But if you now see aligned voids, you may have to now come up with shorter inspection intervals. You may want to think about fixing that. But once you get here, you have to immediately replace it. Now, as you can see here, this classification is in fact based on the distribution of voids and micro cracks. And it's very qualitative, and in my opinion, it's mostly unreliable, especially for carbon and chromoly steels. So if you recollect what we talked about 2 weeks ago, a lot of times you don't necessarily have this void formation occurring until very late in life. A lot of times the creep damage is progressing by plastic deformation, and there's not really much of microstructural evidence of creep damage until very late in life. So it's really not a reliable technique for any creep damage evaluation. And on the top of it, as you know, you're only looking at the surface as well. So if you have anything going on subsurface, you will completely miss it. So in general, this is it has some value where let's say grade 91 weld or something where you have propensity for cracking, where the damage really progresses through void growth. Then maybe there is some value, but in most cases, it really is not that useful. Now, FMR does reveal other high temperature microstructural transformations that you could use sometimes to make a judgment. For example, these are two different heater tubes were the first one here. It's a 9 chrome 1 moly or grade 9 steel, and that's a replica from a heater tube. So what that microstructure here is, what the little dark spots that you see there, those are carbides. So it's basically finely dispersed carbides in a tempered martensitic structure is what you're seeing. So over time with any chrome moly steel, you can have this high temperature microstructural transformation called spheroidization, where these carbides will agglomerate and form like larger carbides, which are lined along the grain boundaries. So in this case, you don't see that. I mean, this is typically what you would expect out of the mill. So you don't see any evidence of a spheroidization. So spheroidization happens typically in about the same temperature range as creep. The fact that you don't see any evidence of spheroidization, I could make a judgment saying, hey, it hasn't, there's no evidence of spheroidization. That suggests to me that it was operating at temperatures below creep becomes a significant problem. So there is little or no creep damage in this material. So that's a judgment that I'm comfortable making. Now, what you're looking at here is a 5 chrome half moly steel. Again, out of the mill, the microstructure should look somewhat similar to what you're looking here for 9 chrome. But you can see here, now you have these big chunks of carbides that are along the grain boundary. So this one has significant spheroidization. So when you see that, well, at that point, all I can say is, well, it has been exposed to temperatures where creep is a problem, but so I can't really say how much creep damage it has accumulated. So that's all I can say here. I cannot really, this does not necessarily mean that it has accumulated a lot of creep damage. In fact, this one, we ended up doing some creep testing of that heater tube later, and it still had plenty of life left. But without uh, actually doing creep testing, there's no way anybody could make a judgment as to whether or not this one has significant creep damage. So the FMR has some value where, if you don't see any notable transformations, you could make some judgment call, but in general, the value is pretty limited. Okay, now that that's out of the way, let's move on to creep testing. And before I go into more details, I just wanted to give just talk a little bit about the terminology, because people use different terminologies when you talk about creep testing. So in general, when you say creep testing, it kind of includes all three of this depending on whom you are talking to. But a lot of times when you say just a creep testing, that's conducted at relatively low stress levels where you don't expect the specimen, you're not trying to get the specimen to rupture. So you are testing it at relatively low stress levels, and you are measuring the creep strain using extensometers. Now, when you say creep rupture test, that's typically conducted at higher stress levels than a creep test, and the test is ran all the way to failure. But you still have extensometers where you are continuously measuring the strain. So you have the outputs are, you have the creep strain and you have the time to rupture here, compared to a creep test where you only have the creep strain measurement. Or you can have stress rupture test, which is again conducted at higher stress levels than creep test, and the test is ran to failure just like creep rupture test. The difference being stress rupture tests do not have extensometry, so you're not measuring the creep strain at all. All you're doing is measuring the time to rupture. And then there is stress relaxation testing, which is not uh, that commonly used, but that in this case, you are basically maintaining a constant strain on the specimen. And then if you do that over time, there will be a reduction in the load or stress relaxation that happens. So you're measuring the stress relaxation there. Now, I'm not going to be talking about stress relaxation testing during this webinar, at least at all. So we'll be spending most of the time talking about the creep test. Now, let's move on to omega testing. So if you look in 579, which is a de facto standard when it comes to fitness for service assessment, uh, when in part 10 where they talk about creep, they 579 just has this one little paragraph in there which talks about creep testing. So what it says is that the MPC Project Omega program has developed a testing protocol to evaluate material parameters required for a remaining life assessment, blah, 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 by performing an Omega test. By performing an Omega test, the remaining life problem is shifted such that the operating conditions up to the time of the test do not need to be evaluated to determine a remaining life. So this is pretty much the only place where it makes any mention about this Omega test. And you have this plot here which shows, so if you have the past operation, you know what the past history is. You could use that. You could do a paper exercise where you can take the properties of the material from 579, do a calculation to see how much damage it has accumulated, and then you say, hey, these are my future operating conditions, and you predict the remaining life. And if you don't have the past operation, it says use omega properties from the test, but it does not say anything about what exactly is this test. It does not provide any additional details on the testing protocol, nor does any ASME or API codes provide any guidelines on creep testing of service exposed components. So this, if you're a fitness for service engineer, you're basically left to your own devices as far as creep testing of service exposed components is concerned. So you need to figure out, how much stress, temperature, acceleration, and testing is acceptable compared to operating conditions. How do you use that test data in the fitness for service assessments? What are the pitfalls, if there are any? So these are some of the things that we are going to talk about today. So before I go on, just a quick recap on the MPC Omega method. We had this slide even during the last webinar, but in case some of you have not attended the previous one, I just wanted to go back and at least address this. So the MPC Omega method, it's based on the concept that the strain rate is a gauge of creep damage, and that the most of the alloys that we use in high temperature applications display very little primary or secondary creep, and most of the time it's residing in the tertiary creep range. So what you're looking at here is a creep strain versus time curve. As you can see here, it's mostly tertiary creep where the strain rate is increasing as a function of time. So if you take this plot here and now you replot that as log of creep strain rate versus strain, you get something like this. And the slope of this line here is omega. And the intercept of that on the y-axis is what you call the initial creep rate. So you could, and this equation here, again, as you can see, is basically showing creep strain versus time equation. And if you know this initial creep rate and omega values, you have all the information that you need to predict the shape of this curve. So this omega itself is the creep damage coefficient, which it defines the rate at which the strain rate accelerates with increasing strain. Now, one thing that you would notice here is that for you to get this omega and initial creep rate, the test needs to be in the tertiary creep regime. to measure these. So, you can see here it drops down a little bit here. That's the primary creep, and then the minimum creep will be whatever is at the bottom point here. And then once it turns back up, that's a tertiary creep. So in theory, you have to be in the tertiary state to measure both omega and initial creep rate. And a lot of times, when you're doing testing, you may have to do this in two different stages, because what happens is, let's say when you're starting a test, um, uh, you can, uh, even though you are assuming that this is it's primarily in the tertiary creep range. When you're starting a test, you need some sort of stress temperature acceleration to get past the primary and secondary stage. You always have a little bit of primary and secondary stage. And sometimes you do the testing in two stages, where you initially start at a less accelerated condition, where you probably will have some primary creep and secondary creep, and you measure that secondary creep strain rate. So if you recollect, so the minimum creep rate or the secondary creep rate is right here at the bottom here. So if you don't have much of primary creep, you could make the assumption that the minimum creep rate and the initial creep rate are kind of the same. So sometimes when you're doing omega testing, you initially test at a less accelerated conditions, you get the minimum creep rate, you kind of assume that that's the initial creep rate. Once you get that, you now accelerate either the temperature or stress to force it to move to tertiary creep, so that you can measure omega. And I'll have later a case study which kind of explains that a little more. And once you have measured this omega and initial creep rate, you can now predict the time to rupture by just taking the reciprocal of the product of these two parameters. So some of the common misconceptions when it comes to creep testing is that an omega test is required if you don't know the prior history of the component, or that when you are when talking about creep testing of service exposed components, that is synonymous with omega testing. Or when you have Larsen-Miller, if you talk about Larsen-Miller parameter, it can only be used for life assessment of virgin materials, because it's primarily only used in design. Now, the truth is, irrespective of whether you're doing a strain-based test like omega or a rupture-based test like LMP, these test results incorporate the prior creep damage. And uh, the rupture test of you can use rupture tests from service exposed materials to do LMP, to do remaining life calculations. Again, I have a case study here which kind of goes through this in detail. So this is a heater tube, 2¼ chrome 1 moly heater tube, which had been in service for 30 something years, operating at about 300 psi, and in the tube metal temperature range of 900 to 1100 degrees. So that's operating in the creep regime there. So, here is a tube that was removed from service. You are looking here at this is a picture of the fire side. So a lot of heater tubes, as you know, you have burners on one side. So it's called either the fire side or the sunny side, and then you have the cold side or the wall side of the tube. And you can usually see a difference even in the oxide scale between fire side and cold side. So when you first remove a tube for creep testing, some of the things that you kind of need to look into is there uh, any loss of thickness going on, because a lot of times you have wall loss due to oxidation from the exterior. Sometimes you have ID corrosion going on. So you kind of look into that. You also look into see how does the diameter of the tube compare to the nominal diameter, just to see if there is any creep related strain going on, if there is any volumetric strain going on. So in this case, you can see that the fire side thickness is in fact lower compared to the other sides, and that's consistent with, as I just said, a lot of times you see more oxidation going on the fire side. And the other thing, you even though you're removing this tube for creep testing, you ideally would want to kind of look at the microstructure and see if there is anything else going on as well. So this is you are looking at some representative micrographs from the tube. So what you see here is for 2¼ chrome, depending on whether it was annealed or normalized and tempered, you can uh, uh, either have kind of carbides in a ferritic matrix, or a lot of times you have perlite. And in this case, when you look at it, the perlite has already spheroidized. So clearly it has been in the temperature range where creep is a problem, but there's no evidence of any other damage mechanisms. A lot of times you see damage mechanisms such as carburization and other things, but there's nothing that's going on here other than some spheroidization. And you also look at the hardness just to see if the hardness is consistent with what is expected in this material. What you're looking at here is a tube wall in cross section from the fire side and the wall side. And you can see here that there's a lot more oxide scale here on the fire side, and it's of course thinner compared to the wall side, again because of the oxidation that's happening on the fire side. Hardness measurements here are within the range of what you would expect for this material. Uh, so again, showing that there is no other damage mechanisms like carburization or significant spheroidization going on here. So moving to creep testing. So a lot of times when you're doing creep testing, we make depending on the component size, we make different uh, specimens of different sizes, uh, anywhere from this is like this one has a gauge diameter of a ½ inch, and going there all the way to like really tiny little flat dog bone samples, which are a lot of times used from components where you don't have the luxury to actually cut out a whole section, but you want to just maybe remove a scoop sample or a boat sample, and then from that you can make these miniature specimens as well. Now, in this case, uh, we made 5 specimens from the tube section, 4 of them hoop specimens from the fire side. So as creep is affected by stress and temperature. So in a tube, heated tube, under internal pressure, you have the highest stress along the hoop direction, and the highest temperature is on the flame side. So the argument is the most creep damage would be along the hoop side, on the fire side. So you test more than one just because of the variability associated with creep testing, and you would want to make this decision based on more than one specimen. So 4 specimens are made along the hoop direction from the fire side, and then you make one axial specimen from the wall side. So that is meant to be a reference sample to the degree possible, a sample with minimal creep damage. So all the tests are done in our creep lab in Cincinnati. Now, I'm not a test engineer, but I have huge admiration for those who are. It's not trivial to control and measure temperature and displacement over a long period of time at high temperatures. So what you're looking at here is like the data collected for one of our samples. As you can see, this is going on up to about 650 hours, and you can see that this is the temperature controls. Temperature variation is like less than plus or minus zero point 0.1 over that time period at 1450 degree Fahrenheit. So my colleagues here, Shannon Reed and Ken Sanaki, they designed and built controls to control, monitor temperature and displacement, and with daily updates. So this is just a screenshot of what I get every night when we do creep testing. So in this case, so we did creep testing on 5 specimens machined from the tube. Not all the tests were ran to rupture. So you can see they were run at different temperatures and stress levels. And what you're looking at here are 2 of the strain versus time curves. So this test, as you can see, was ran all the way to rupture. Now, earlier I showed how to measure omega and initial creep rate by plotting log of strain rate versus strain. But you can also get that omega and initial creep rate by fitting your strain versus time curve. I had that equation in one of my earlier slides, but you could fit that equation to the curve. And in this case, so here M2 here is the omega parameter and M3 is the initial creep rate. So you could fit the test data to this omega equation to get the omega and initial creep rate. So this test was ran all the way to rupture. This one did not go all the way to rupture. It was terminated after about 1200 hours of testing. And as I said earlier, once you have this omega and initial creep rate, we could use that information if you want to predict the time to rupture for that particular test. So as I said, the omega parameters are determined by curve fitting of the test data. So that is shown on this table here. So these are the 5 different specimens, the temperature and stress levels that they were tested at. So this is the initial creep rate, the strain rate that we measured from the test. That's the omega. This should be omega, sorry. This shows the omega values that we measured from the test. And once you have this initial creep rate and omega, what now you have to do is these 2 equations here are directly from 579. So 579 gives you the omega and initial creep rate equations and the coefficients here, this b0, b1, b2, b3, b4, those are the initial are the omega coefficients that are given in 579 for that particular tube material. In this case, 2¼ chrome steel. S here is this stress, T is the temperature. So we know both of that. So what we do is once you, let's say, get the omega parameters from the test, you could now take this omega here and you could put that in here. You get the B coefficients from 579 for 2¼ chrome. You know the temperature and stress at which you tested. So the only unknown here is this delta omega CD. Same with the initial creep rate. You measure the creep rate from the test. You get the A coefficients from 579 for 2¼ chrome. You know the temperature and stress. You can now back calculate this delta omega SR. So these delta omega values account for the deviation in material properties of your component material from the nominal properties of 2¼ chrome steel. And the delta omega SR, if you calculate a value that is a negative value, that basically means that your material is creeping at a higher strain rate than what is expected of an average 2¼ chrome material. So that would mean that it is, it could be slightly degraded. And with omega, if you are getting if the delta omega CD value, if you're getting a negative value there, what that means is your material is more creep ductile than average 2¼ chrome steel. And if it's positive, that means it's more creep brittle. So ideally, you want it to be negative, because if it's creep brittle, that means it doesn't have that much ductility. Now, The other thing, once you have that information, the other thing that you could do is you could now take that, again, the temperature and the stress levels, and you could now, the time to rupture, either the actual time to rupture or what you can estimate based on the omega parameters. You could now get that time to rupture. And once you have that, you can calculate the LMP constant based on WRC 541. And once you calculate that LMP constant, you could now plot that against stress, the Lasser-Miller parameter and stress. So what you're looking at here is the line here is the LMP curve for WRC 541. Excuse me, LMP curve for 2¼ chrome 1 moly per WRC 541. And you could now plot that. So against, you could plot your data points, and now you can see how the rupture properties of your material in the surface exposed condition compared to that of nominal properties of 2¼ chrome. So you could also do the same thing with the old API 530 LMP curves, where you can, again, you either have the actual rupture time or the estimated rupture time. You use that to calculate the LMP, and once you have the LMP, uh, you can now, what you're looking at here, this here is the LMP average curve for 2¼ chrome. The dotted blue line here is the LMP minimum curve for 2¼ chrome. And these are the data points from the test. What's interesting here is that, so as you can see, even in the service exposed condition, even though it had been in service for 30 something years, the properties of the tube material is still within the range that's expected. In fact, it's still better than minimum properties. So remember that when you're designing heated tubes from API 530, at least in the earlier days, you are designing them assuming that it has the minimum properties. And what this is showing is that even in the service exposed conditions, it has better than minimum properties. Now, that does not necessarily mean that it has not accumulated any creep damage in service. For all you know, because we don't know what the properties of the tube material was on day one. So it is possible that, when they started out 30 years ago, maybe the properties were up here and it is degraded now. This is what it is now. That's possible. Or it's possible that it hasn't accumulated any creep damage and this is what it was. It hasn't really changed much. But irrespective of that, you could almost at this point say, hey, I have these tubes and these are the properties as of now. And you could kind of reset the clock. Using these properties, you could in effect assume that this is a new material with these properties, as long as there are no other damage mechanisms involved here. And you could use this to come up with an LMP curve that is specific to your tube material. And that's what I'm showing here in this table, where you could come up with the coefficients similar to what is given in 579. But in this case, these coefficients here are specific to your tube material rather than what's given here, rather than what's given in 579 for average or minimum curves. So once you have this, how do you calculate the remaining life? The remaining life of a heated tube is controlled by three different things. You can have creep, primarily it's creep rupture is what controls the damage, but you can also have you need to look into the elastic life, which is, if you have somehow a pressure upset in your tube where the stress levels go above yield at that temperature, you can just have a time independent failure. So that's something that you need to look into. You also need to look into what the retirement thickness that's set by the owner. A lot of times, if you are operating at milder conditions, when you're doing a creep calculation, it might show that the creep life is extinguished only when the tube thickness gets to like 0.0 0.05 inches thick or something, or even lower. But at that point, it could be structurally unstable as well. So a lot of times, the retirement thickness is typically set at 0.1 inches. So you kind of have to look at which one controls. So what you're looking at here is remaining life as a function of tube metal temperature. So you're doing the creep damage calculations using Omega, WRC 541, and the old APA 530 methodologies. And we are also calculating the elastic design. We are calculating how much time it takes to get to zero point 0.1 inches wall thickness based on corrosion. And as you can see here, the life here is controlled by creep. But the one thing to note is that, as you can see, irrespective of whether you are doing these calculations using MPC Omega or WRC 541 or APA 530 old edition, they are all kind of in the same ballpark. There's no practical difference between the remaining life calculations per these three methodologies. Now, these things are almost overlapping, but in some cases you see a little more difference, but in general, they are almost always in the same ballpark. So moving on, now I have a couple more case studies, but I'm not really going into as much detail as I did in the first one. This is just to give you just some insights into some of the other things that you need to consider when you're doing creep testing. So this is a carbon steel reactor which had been in service for a while. And when we did metallography, you could see that these black dots that you see here, that's graphite. Those are graphite nodules. So this one has undergone the damage mechanism called graphitization, where the carbon comes out of the solution and forms graphite nodules. This, what you're looking at here, this black nodules are graphite. Now, so graphitization reduces the creep strength. And based on even my experience testing, I've always seen a drop in the creep properties when you have graphitization. Now, graphitization can form in two different ways. One is like a random graphitization where your component material has just this graphite is formed, nodules are forming, and they're not necessarily oriented in any direction. They're kind of randomly dispersed, which reduces the creep strength, but it's not that bad. But what is worse is what you call aligned graphitization or eyebrow graphitization. So that usually happens along the heat affected zone, as you can see here. So that's a weld that you're looking at here. And the heat affected zone, you can see the string of graphites kind of lining that. That's usually pretty bad, especially if you have loading that's in this direction. If it has axial, if it's a girth weld and you have axial loading, this could be a problem. Now, if you are going to do creep testing, how are you going to do the testing, right? So you can, of course, do testing in the base metal, but how do you check for if you have this aligned graphitization going on? It's not really practical. You really cannot make a specimen from the heat affected zone. So a lot of times what's done is you make a cross weld specimen. So now you're making a specimen. So this, what you're looking at here is a cross weld specimen. So there's a weld right there. So you have the weld here. So your graphitization, aligned graphitization will be right here. And then what you do is you do the creep testing on a cross weld specimen and you compare the rupture properties of your cross weld specimen to the base metal specimen. So so here is a cross weld specimen after testing. As you can see here, it failed right along the heat affected zone because of that aligned graphitization that was there. So what you're looking at here is an LMP curve for showing the average and minimum curves for carbon steel along with the data points from the tests. So you have 4 tests from the base metal where the properties are still better than minimum but lower than average. But you can see that the crosswell specimens are inferior. They have inferior rupture properties compared to the base metal specimen. And that's because of that graphitization that was going on in the heat affected zone. So once you have these results, you could now use that information to calculate what you call a weld strength reduction factor, which can be incorporated in your analysis. In this case, we this was a reactor where we had a finite element analysis, finite element model, and we incorporated that weld strength reduction factor to account for the fact that the weld properties are inferior compared to the base metal. Uh, so moving on to the third case study where this was a type 347H stainless steel heater tube. As I mentioned earlier, omega test sometimes is done in two stages where you first have the initial stage at a less accelerated condition to measure the minimum creep rate, and you kind of assume that the minimum creep rate is the same as the initial creep rate. And then you accelerate it to force the test to go to tertiary creep so that you can measure omega. There's no way you can measure omega uh, unless it's in the tertiary creep range. So in this case, the stress level was about the same as the operating stress. And that's ideally what I think MPC omega um, recommends, where you test at more or less the same as the operating stress to avoid any additional primary creep that forms. So it was at the operating stress level, initial temperature was 1270, which was higher than the operating temperature actually. But then we bumped up the temperature level to 1400 after we measured the minimum creep rate. So let's look at those. So this is the first part of the test where it was ran at 1270 and 10.3 KSI, where we measured the minimum creep rate, which was 6.5 e to the minus 6. And once we got that, the temperature was bumped up to 1400 degrees. And that's what you're looking at here. I have re-zeroed this. That's why this is starting from zero again. So what you're looking at here is a strain versus time curve once the second stage of the test. Now, what you're looking here is the log of strain rate versus strain that I talked about earlier. What's interesting here is that when you look at it, so there is it coming down, that's a primary creep bar, and then it turns around. So, that's a tertiary creep range, but you don't necessarily have one nice omega value as I showed earlier. Instead, it comes up, here, if up until you get to about 0.015% strain, 0.015 or 1.5% strain, excuse me. What you see is that it's a very high omega value, but then it kind of turns and then it settles down to a omega value of 18. Now, if you look at this, and if you just go and get the 347H properties and you try to see what these different omega values mean, uh, uh, you would predict that this delta omega CD value of close to plus 1.0 to get a omega value of 178. Whereas, at delta omega CD of 0, that means nominal properties, well, that's close to 18. So what's interesting is here is that somehow the omega value is not constant here. It's actually changing during the test. And if you were to just measure this creep rate initially, and then you uh, increase the temperature to accelerate and you start getting the tertiary creep, and if you were to terminate the test here and then use that information in your remaining life calculations, you would have been wrong, because you would end up being highly conservative there, because your calculations would say that you don't have much ductility there. So what's going on there? Being a metallurgist, I thought my initial thinking was, oh, maybe there might be some microstructural changes that's happening during testing. So the Omega database is purportedly generated using service age materials, right? So what if your material was not necessarily service age, or any changes that would happen at high temperature service have not happened at? And what if those changes are happening during the test, right? So here is a micrograph of that tube before testing, and you see a austenitic structure as you would expect in 347H. And here is that specimen after we perform the creep testing, and you can see that there's what you call sigma phase formation happening here. So sigma phase is an intermetallic iron chromium intermetallic that forms in stainless steels at high temperatures. So in this case, there was sigma phase formation happening during testing. So is it really what was causing the change in omega? So just to find that, we just bought a type 3 or 4 stainless steel bar stock. And this is the micrograph showing what it looked like as fabricated. And then we just aged that material for 100 hours at 1400 degrees. And you can see that in 100 hours, it forms quite a bit of sigma phase. So then what we did is we made two creep specimens. The first specimen was tested at 1400 degrees and 7.5 KSI. Again, this is a brand new bar stock. And the second one was tested at the same conditions, but after soaking at that temperature for 100 hours. So the load was applied 100 hours later. And here is sample A, the creep curve here, and this is the strain rate versus strain curve. And this is for sample B. And you can see here clearly you have, in this case for sample A, which was not soaked at temperature, where in this case, the sigma phase was actually forming during testing. You can see that similar behavior as we saw in that heated tube, where initially there was a higher omega and then it kind of came to a much lower value. Now, this one was soaked for 100 hours where you had formed at least some omega, some sigma phase. And you can see that it's not, so the initial omega value here is only half of what you see here. Now, my thinking here is that the omega formation, the sigma phase formation was not complete even after 100 hours, so you still had more sigma phase forming here, but still you can see that this kind of suggests, this indicates that what is going on in this case here was that you had sigma phase forming during testing. So that's another thing that you have to worry about. Some of the things that you need to know when you are trying to do creep testing. So the concluding remarks here, creep testing is a valuable tool in the remaining life assessment of service exposed components. And there are multiple approaches that can be used for creep testing and remaining life assessment of service exposed components. There's no notable advantage for any one method over the others, especially when testing components under simple stress state like a heated tube. If you are testing, if you are removing material from a pressure vessel with somewhat complicated geometry and you want to do a remaining life assessment, you pretty much need to use the MPC omega method, because that's the only one that allows you to the constitutive properties in the analysis. And microstructural changes during testing should not be overlooked, because not all high temperature components are service aged, and you might be introducing some, you want to make sure that you're not introducing some microstructural changes during your creep testing, which might throw off your results. So that concludes our talk. In case you are still craving for more creepy stuff, we are planning on a one-day creep workshop in our Houston office in early October, tentatively October 7th, but we will be sending out an email later regarding this, but that'll go into a lot more details than what we could cover in this 2 1-hour presentations. But that's so yeah, we'll be in touch regarding that. But that concludes my my talk.